I want to close off this lesson by saying a really quick note, and then I need to show you something which will emphasize why it's important that you are drawing your graphs really accurately, and why if you have a template, you are actually at an advantage, I think. The first thing I want to point out is, what if we just established this lesson without integrals and so on, okay? At this stage in the course, you know how to integrate a lot of things. A lot of things. Like in fact, as Extension 1 students, you pretty much know how to integrate everything you'll ever need to do in the Extension 1 course. That's a big deal, okay? Extension 2 people, you're a little ways to go. I mean, you have a whole topic called integration, but we have a whole bunch of things. For instance, we know all of these. Anything that is a straight polynomial, we know how to do. We also know how to integrate a whole bunch of rational functions. The simplest one we know is this one. What kind of function are we going to get if we integrate this guy? Think carefully. This is the log function, right? Now, I'm just going to, for now, I'm not going to worry about the absolute value, because all I'm trying to draw attention to is the fact that even though what I started with was something that's just algebraic, right? It's x's, there's a division happening, and everything that's in a similar kind of, any polynomial that's combined in this way will also land you in a log function. That's kind of surprising, right? It's a little bit like, yeah, I just started with polynomials, and when I put them together in interesting combinations, you end up getting logs. And then here, we've gone even further out. Like, it wasn't that surprising that if you differentiate sine, cos, and tan, which are trig functions, you get more trig functions. Okay, sure, that's in that one sphere. But now, like, this is just algebra. It's just algebra, and when you integrate it, you end up in the trig sphere. That's kind of weird, okay? But also very interesting and surprising. Now, that's the first thing I just want to draw your attention to. The second thing is I need to make an argument for you for why your graphs need to be really good. And not just because your graphs should be really good of their own accord, but there are going to be some questions you cannot answer, full stop, if your graphs are no good, okay? This is all about just integrating with respect to algebra that lands you in an inverse trig function, okay? However, I want you to contemplate this question with me. What if I were to give you, say, okay, here's an example. Of this, okay? Now this, despite how I've built it from all the same building blocks that we've been dealing with this lesson, this is a whole different beast, isn't it? Like, this is not you start with some algebra and you end up with an inverse trig function. This is starting with an inverse trig function and saying, well, where are you going to land? Okay. Now, it's a big clue to you that this is not just an indefinite integral. I've got some values here, and those values are actually very, very important. Okay. So this is a definite integral, which means what are definite integrals about? Like, what kind of problem did we come up with to solve? They're area, right? Area under a curve. So this corresponds to a picture. Can we draw it? Let's just draw it briefly. It won't take you long. Go ahead, put yourself together a set of axes and draw your picture. Okay, now here's my regular, unmodified cos inverse graphs, right? So I should label it as such. Now, what area is being referred to here? I'm going from -1/2 to 1/2, and I know exactly where that is, so I can say, okay, it's going to be halfway that way and halfway this way. So now I can actually paint on what area I'm being represented by this definite integral, okay? So I'm going from -1/2, that was the wrong color, to 1/2. This is the shape I've got, okay? Now this shape here, this shape is weird. This shape is weird, right? How am I going to deal with this? Now you have some choices. You have some choices. I don't know at the moment, it's not in my toolbox to integrate an inverse trig function, okay? Okay, so I just can't get an answer straight out from all of this stuff that I've seen. It's certainly not in the reference sheet. Okay, but I do know how to integrate regular trig functions, right? Regular trig functions, and I know that this comes from a regular trig function. So here's one trick I could pull, and I will show you like proper examples of this later, but it's quite involved. If I turn this sideways, right, and turn it back into a regular trig function, it could look something like this. This is like a part of the cos graph, right? It's a part of the cos graph. It's this part. If I draw regular cos and that domain, I go from 0 to pi. There it is. Okay, so that's where I end. Now, where is that on here? Well, here is 1 and -1. Do you agree with that? So what I've done is I have to look at everything sideways. So here's a half and -1/2. So I've got the same kind of boundaries, okay? And now if you turn your head sideways, here's what I'm after. Do you see that? Now this is still a bit messy, okay? But I can deal with it if I want to by saying, look, if I slice it that way, what I've got to the left is a rectangle. And what I've got to the right, I can deal with that just with my normal integration tools. I'm gonna have to slice this up into a positive part and a negative part, but I can do it, is my point, okay? This is fine, but it's messy, it's involved. Even without me actually starting to put some of the algebra on the board, you're like, oh, this is gross, okay? If your graph is decent, there's something smarter you can do here. Why don't you have a look? Cos inverse is funny because it doesn't have odd or even symmetry, right? It doesn't have odd or even symmetry. However, as all trig functions do, it has a marvelous amount of symmetry to it. And you'll see it if your graph is any good. Are you getting my point yet? Okay. Watch. These two parts together, how do they relate? Well, I hope you notice that this distance and this distance are the same. Do you notice that? Those widths are the same. And you have a look, see how this part decreases and this part decreases, right? Look carefully at the concavity. Do you see that these two pieces actually fit together? They actually fit together. If I draw upwards here, I wonder if your graph is good enough to be able to see that this area over here and this area over here are identical. Do you see that? Now, if you're like me, I started off not being able to draw these very well. So what I just showed you, right, I'll color it in a little harder so you can see. What I just showed you is not obvious at all because I haven't mastered my curvature yet. Hey, there's an easy way to get the curvature. Exactly right. Every single time, so that this thing is obvious to you. Okay, if that's the case, how am I going to work out my answer? What shape have I just created? It's a rectangle, right? It has a width of half a unit. And it has a height of pi units. So this insoluble problem before turns out to be marvelously simple. If you understand the geometry and your graph is good enough for you to take advantage of that. Okay? Now you might say, man, that's tough. Well, yes. However, number one, the other way is tougher. And number two, it is absolutely, oh, I turned it off. That's a shame. It'll wake up. It is absolutely possible for you on paper, especially if you're using a template, to be able to take advantage of that geometry. Let me show you if this warms up quickly. The first time I encountered a question like this, yeah, there it is, okay. The first time I encountered a question like this, my graph literally was not good enough to be able to see the symmetry at all. It wasn't symmetrical, okay? But when you have a look at it, you can say, yeah, all right, if you got, like I drew this with a template because I wasn't able to draw it at that stage. This is a few years ago. Accurately enough to make that argument. You use a template if you have to, so that you get the shapes right, until such a time as you master being able to draw a trig graph that well. And I don't know, it might take you a while, okay? So, I believe I can't remember, it's like towards the tail end here, it's 13, 16 or 18, I believe. And the question will say, using a graph and symmetry, evaluate, and then they'll hand you, it's under the board, they'll hand you a definite integral, such as this. And there, you have to draw a graph. Without my graph, I can't say this, right? I'm dependent on my graph and the demonstration of my shifting of areas to be able to justify that. Okay? Any questions? Say Say it again. No, not really. It's such a tangled disaster that it's so much smarter to do everything you need to do if you ever wanted to integrate an inverse string function. You'd do it this way, right? Or you'd rearrange such that everything is in terms of regular string functions. You use inverse properties rather than those properties.